Okay, good evening, everybody.
Good evening.
And yeah, welcome to the class. And I hope you guys still remember the new deadline for the exam. Um, Although take the relatively flexible way, will be due tonight. Okay. Um, I will look at your submitted solutions, recent days, and give your feedback on them. Right. And let me go straight to our progress and the materials we're going to talk about today. Um, okay, so firstly, let me go to share the screen on our progress. Um, so on our information, let's look at the syllabus. Okay, so the syllabus we used, we have been some students ask me what the for the third questions in the exam. What's the case studies we're looking to compare with? You may or may not miss the last class. The case I'm talking about on the March 17th is basically the T-bill, the Treasury bills case, okay, which is the most recent ones. So that's just want you to remind you here. So if you went through this problem by your own self, you will find that the ideas is almost the same. I just simply let you to replicate the procedures with the new data. Okay, that's it. And I just to reemphasize the importance the last class we're doing here. Actually, recently I do my own research. I also find similar things. When we talk about time series stuffs, right? We're looking for forecastings, right? We're looking for predictions for the next period, what's going to be the value. So sometimes you can use the variables by its own self. For example, if you want to predict the stock return, if you want to predict the earnings of the company, you just simply use the past history, make the forecasting. Sometimes you might want to use some other variables to make predictions. For example, I want to make a prediction on the GDP on the time series. I think GDP is the function of, say, for example, volatilities, technology, income, right? Something like that. So you can put those variables on the regression, but the regression also be performed on the time series. Actually, this is actually indeed a quite complex problem. So in the case study last class, if you still remember clearly, we use the one variables to predict another one, right? It's actually, this is a kind of a regression, a traditional regressions. However, we find that after the regression, the residuals is not perfect. There is a serial correlation on the time series. So what we do first take the difference to make them stationaries. And the second, we model the residuals, the arrows, in terms of the moving average, right? So you can see it's a very a good comprehensive, the exercise on this topic, which is different from our traditional, say, MA or AR, just simple those steps, right? So this is relatively comprehensive. And so this week, we're going to talk about a review of capital markets and derivatives. And the week 11, we're going to talk about asset volatility models. So this is a caveat on my schedule here. So my purpose for today's class, I basically simply want to review the capital markets and the derivatives, for example, like Black-Scholes models. However, I think it will be stretching out to spend the 2 hours to simply talk about some old financial knowledge. So I will just give a very brief review on those steps, and I will talk about how those things relate to assets volatility models. And I will also talk about what the meaning of assets volatility and why we need such models. I think basically over next few weeks, we'll focus on those kind of steps. Okay, and then we'll go to the final exam. If we have time, for example, if the assets volatility models we can finish relatively quickly, we can, I think, introduce something more interesting stuff. For example, I might want to introduce something like the artificial intelligence technology, AI, maybe machine learning, or maybe some high frequency trading, something like that stuff. So if time allowable to do that. Okay, so today we're gonna just look into the assets volatility. So that's basically I will combine a very brief review on the derivative as well as assets volatility models. Okay, the ARCH models we were discussed today. Okay, so this is basically my schedules. Next class I will discuss the homework. The exam we're going to talk about. Okay. So from this point of view, in the next few weeks, I might well give you another assignment, and final exam. So I will expect the final exam. I would like to continue to take the form of like assignment, give you relatively flexibility instead of sitting there 2 hours, finish some things. So I think especially for oral class, I think that way maybe not very good. All right. Okay, so if you have any questions, just freely let me know. And let me go to the course materials. Let me pull out the Okay, so today I'm gonna talk about the volatility models. Okay, these slides, the univariate volatility models, conditional hydrostochastic models. Okay, I believe if you look those kind of stuff, your hands will be blown out, right? So it's the words so maybe necessarily or unnecessarily complex. Okay, so I think this is a very I will introduce gradually as we approach previous months, and I hope you relatively comfortable with my way to introduce those stuffs. And I want to keep some things, rule out something very complex and just keep something very simple and relatively straightforward. Focus on the hands-on, the coding exercises, interpreting the results, something like that. Try to avoid the statistics too much. Okay. So the first question, let's forget about the title. Okay, the title, if you look at the first glance, is very horrible. Right, I'm pretty sure. And the univariate basically simply means that there's only one variables volatility. It's similar to our linear time series model we introduced before, for example, like autoregressive, like the moving average. There is only one variable. That means the dependent variable by itself. It's just simply the time lags. There's no other variable. If there's other variable, we will call that regression, right? So this is univariable. And so today we're gonna firstly talk about why we need to estimate the volatilities. what exactly the volatility means for financial markets. And then next, we're going to talk about why we call them conditional heteroscedastic models, why we give such a complex name. Okay, so the first question, so what is the volatility of assets? So the answer is a conditional standard deviation of the asset's return price. Okay, so that's it. All right, for example, if I give you in the Excel, all right, Excel, and let me see. Um, I'd like to give you some examples, maybe better. So, okay, so let me share the screen for you. For example, this is the Excel, right? Excel. I just simply copy the IBM data in our previous classes, and I randomly pick a couple of observations, right, from the data, and I copy here. So this is a date. This is the price, right? And this is the bid ask price. This is the returns. This is the return. I think this is a return. I'm sorry. The format is a little bit chaos because this is a text format, and I copy to the Excel. So if you look at those returns, this is the returns, right? This is a equal weighted market returns. This is a S&P 500 returns, something like that. So there's could be like a -5%, -2%, +5%, 10%, something like that. So we understand those are levels, right? Those are levels. So what is the volatilities? You probably say, okay, so I have those observations, and then we just simply calculate the volatilities, right? Firstly, work out the mean, and then calculate the deviation, and take the square root. This is our undergraduate way to calculate the volatilities. However, there's a problem. The problem is that if you calculate the volatilities using those data, all right, and I would say such a volatility is only one number, of course, right? Because you have such data observation, I want you to calculate the volatility. You will only have a one number. This number will be the volatility. Is it meaningful? Probably not. The reason is that in the reality, in the real financial markets, the volatility is such a parameter you can't observable. You can't observe. Each, every day has its own volatilities, and you want to know. So you will find this problem. For example, on the 1968, January 31st, we have a volatility. We should have a volatility corresponding to that day. On the February 29th, there should be a volatility corresponding to that day, right? So each day should have volatility, and not mentioned here, I think this is a monthly data. You can see this each month have one observation. So how do we do that? Okay, for example, this is one in 1968, January, last day of January. How do we quantify the volatility in this period, in the January? Of course, the natural way will be that we need the whole month's data daily. And then we will probably have like 22 trading days. And then we use the 22 trading days stock returns to calculate the volatilities. And then use that volatilities as this month. So similarly, for each month, we will have volatilities. So you can find that if we want to calculate volatilities, we need more delicate data. We need a high frequency. That means for short time intervals. All right, because when we calculate volatility, you need a lot of data, not only one data. You can't do this, right? For example, if I want to know what is the daily volatilities, for example, like today, what is volatilities? If you only have one observation for today, for example, when the market is closed, you only have one observations, and you can't calculate volatilities. So what you're gonna do? You need to put out, for example, every hour or every minutes the stock returns, and use such a high frequency data. You have many observations per day, right? And work out the volatilities, and that volatility will be your today's volatility. So if you if you want to calculate volatility, assets volatilities, you need more data. That's it. Okay, so this question here. Now, if I want to calculate the volatility of the IBM stock for each minute, is it possible? I think so, because
If you
every
like
minute,
break it to seconds.
perfect, similarly. And indeed, the stock trading nowadays is very fast. It's a lightning speed. Every second, there's a thousand of transactions happens, particularly for a big company like Apple. So in this case, we always can find, the more delicate time calendars, more finely tuned time intervals for volatility if we have such a data, high frequency data. Okay, so now there's a couple questions. But the question is that in theory, what exactly the definition of volatility? We don't know, right? I mean, the volatility, we need a more and more data, more and more data, but what exactly the volatility means that? Does it exist? That's the things, right? So we only can calculate volatility using the more data frequency. For example, if I want to calculate today's volatility, I can use, say, 8 hours, 8 observations each hour, I get the value. Or I can use, say, 60 minutes per hour times 8 hours is going to be 480 minutes stock return observation. Or I can use more finely, time intervals. So which one is correct? That's the things. So we never know what's the true volatilities, because the volatility only can be realized when people buy and sell this. That sounds like, for example, you know, um, say I'm running a firm, a company. I have real assets, not the financial assets, the real assets like the machines, like facilities, all right? This is assets, a fixed assets. I might want to ask this question: what is the volatility of the value of my fixed assets? You probably find it is very hard. The reason is that the real assets never trade at high frequency as stock, right? They probably for nearly 10 years, nobody buy and sell this. So if the real assets, nobody buy and sell this, there is no volatilities you can observe, right? So in this case, volatility by itself is actually very abstract, and we only can estimate that using some the sample data, right? Okay, that's it. So I just want to brag a little bit on that, and let's go back to our formal knowledge here. So, and when we talk about the conditional standard deviation, simply means that the volatility today will usually depends on yesterday. It's similar to the autoregressive, as the intuition tells us. All right. For example, if the recent days there's a political uncertainty around the world, and highly uncertainty several days ago, and I'm pretty sure such uncertainty will be still has influence in recent days. So there is a conditionals, right? Okay, so why is volatility important? has many important applications. So we will see why we look into the volatility modelings. One thing is option derivative pricing, like Black-Scholes formulas. Okay, has anybody learned the Black-Scholes formulas before, or have a chance to take a look into that?
Yeah, I have, but I would have to see it again for me to remember it.
Sure, that's what I'm doing here. I will show the web page and let's see again. So let me see what's the horrible formula looks like. Okay, and okay, so let me go to the website. I think the Zoom teaching is very good because it can always goes to the very conveniently goes to the website, right? I just simply go to the Wikipedia, all right, and I open the Black-Scholes model. So what is the Black-Scholes model talk about? I know some people maybe know, some people never know, but it doesn't matter. We will not test you. We will not test you in the homework or exam or whatever, because this is just a kind of like a background knowledge. But of course, if you understand, that would be fantastic. Sometimes you need some financial knowledge in your mind. So Black-Scholes model is kind of a model to tell you how to calculate an option values, call option and put option. So what is option? Option is kind of derivative, very classic derivative. All right, it's similar to the insurance. That means if you want to buy a stock in the future and you are fear of the stock price too high, you can buy an option instead of a stock in itself. Because if you buy options, you can lock on some upper price, right? If the stock price over that, you will still buy the stock with the agreed upon fixed price, right? If the stock become cheaper than the price you locked, you can give up the options and directly buy the stock with the cheaper price at that time. This give you definitely very good hedging strategies there. But the question is here is the option is very hard to value. Why? Because say if you want to value any financial assets, the core asset is time value of money, right? You basically discount up the future value to today's. But for option, you will never know what's gonna be stock price in the future, all right? And then work out what's the payoff, and then discount it to today. And even you discount, what is the discount rate? That'll be perplexed. You want to use the risk-free interest rate? No. Option is very risky. It's riskier than the underlying stock, of course, right? Because it's derivative. If it's risky, the discount rate should be significantly higher than the risk-free rate. And what is that? You don't know. You don't know, right? Unless you know the riskiness of the option, then you can figure out what discount rate. But you can't do this because what I'm doing right now, I'm trying to value this. It's very perplex. So the Black-Scholes these two people that smartly design some strategies. Okay, it's not our business, and it come up with some formula like this. Okay, so if I want to calculate the call options, that means the option you use to buy something, you'll figure out the price will maybe go up, equals something like this. It's kind of a normal distributions of something, normal distribution of something. ST is kind of the assets you want to buy actually covered by the option, for example, like a stock. And the K is kind of the price you negotiate for fixed, all right? And this one you can think about like under the continuous time, the discount rate, all right? So let's look at the parameters. This is actually very popular used in the Wall Street, even for this decades. That's why they get Nobel Prize for that, all right? And this is the big T represents the entire time length, the life length of the options, right? Because you can't say, okay, I want to hold my options for 50 years. No way, you can't do this. You only can make your decision in a certain time, like say 1 year or 2 years. You can't take it too long, all right? So the big T here represents the maturity. And the small t here represents the current time at which you want to value them. This is LN functions. This is a risk-free rate. This is volatilities. Volatility of the underlying assets, that means the stock, right? So the question is here. We want to estimate this one. We want to estimate. Why? For example, look at these formulas. I think the time t, current time t, are known. Stock price in the future, we don't know. We don't know. We only can guess. The K is a negotiable price, fixed. We can buy. The upper price is known. So you can see the only unknown is gonna be the volatility, except for the future stock price. So it's gonna be the volatilities, right? So you will see it is very useful if you can estimate the volatilities as accurate as possible. Some people say, can we try to predict the stock price? I would like to say, it's kind of a futile. It's very hard. You only can estimate some best range, but it's very hard. But forecasting the volatility is a relatively easier job and sometimes very accurate. Okay, so that's why this is the formula we use here. So that's the so-called Black-Scholes models. All right, and again, so for example, when I talk about the stock volatilities for some time t, it's going to be tricky. As we mentioned, you probably need as many as observations as possible and a high frequency data to calculate the volatility for each time. And this time depends on the minutes, hour, monthly, or daily, right? So these things. And risk management, value at risk. I will not present here. The value at risk is kind of risk management that people need to work out what is going to be the maximum loss under the 5% chances, right? So this is sometimes we need asset allocation, all right? Minimum various portfolios. I will not go to details, but we know when construct the portfolios, we need the minimum variance portfolios. What does exactly means? That means I want to construct a portfolio, which is include several stocks or any other type of securities. I want to get the minimum variance because we know that different assets has different riskiness, randomness. Usually they can cancel to each other. We call them diversification. And then we're looking for the minimum variance. All right. So in this case, you need to make estimation on the portfolio performance in this sense. And any other forecastings. Okay, so in this case, you can see the volatility will be very important for the option pricing and the risk management field. Okay, so the question here, how to calculate volatility? This probably go back to my original points I mentioned here. Several versions of sample volatilities, but the conditional standard deviation is commonly used. Okay, so use high frequency data. French Stamboff, the several people in 1987, the paper, they find that the realized volatility of daily log returns use intraday high frequency log returns. So in their paper, try to understand the stock market. It's not our business to understand, but they use the realized volatility. Usually when we talk about the daily volatilities, we call them realized because daily volatility is very hard to get in 1987. Because at that time, I would say that the stock exchange market, like NYSE or NASDAQ, they don't have the record tape to record each second transaction price. They don't allow to do that at that time technology. They don't know that. I think since the 1990s will be fairly common for the stock market, exchange market to begin to record high frequency data on the second levels. Okay. Sometimes there's another way to express volatility instead of just simply the calculate so complex stuff. We can simply use the range, right? That means the daily high minus daily low. That is also doable, all right? So let's give you the kind of the gap what was the deviation. This is another way to express volatility. And of course, the more frequency data we have, the more accurate, right? If you only have like 2 observations, one is the morning, the other is afternoon, definitely the results will be very vague, right? Okay, so the next is implied volatility of the option status. Anybody have heard about what is the implied volatilities? Never mind. So let's go to Black-Scholes model here. Let's continue to look at the Black-Scholes model here, okay? And what is the real line? What's the implied volatility? So this model is called, can calculate the put out, the call options. Now, the interesting part here, the call option price is available in the market actually. You can observe that. You don't need to estimate using the Black-Scholes model. You simply, you know that. So what are tasks? Our task can use the known call option price, substitute into here, and work out what is the volatilities. Work out this volatility. And this volatility is assumed the Black-Scholes model is correct. Then we calculate the implied. So that's the implied. And this implied volatility definitely will be different from true volatilities. The reason is that the formula by itself has a lot of drawbacks. So that's why we understand if you use the true actual call option price, the standard deviation you calculate out is not the correct one. It might be close, right? And in that case, we call this implied volatilities. Okay, and the implied volatilities has been very popular at the products, we call them VIX, or at CBOE with the Chicago Board of Exchange. If you look the VIX, if you look the everyday financial news media, you probably will know that there is a so-called VIX index to measure the degree of extent of the panic of the market. So again, so you will know that the VIX is actually indeed an implied volatility from Black-Scholes model, and we want to calculate what is the, if the model is correct, what's going to be the volatilities, and that represents the market uncertainty. Okay, econometrics, let's skip that. So in this chapter, we might be talking about some high frequency data to compute realized volatility. That means using to look into what the daily volatility is, but we will leave this for this future discussion if we have time. Okay. So now let's look at some low frequency data. We need to understand some very basic relationship. Okay. So in most applications, volatility is annualized. It's similar to the returns, right? If I tell you the interest rate, if I tell you the return, usually the quoted returns or interest will be annualized, and similar for the volatilities. So this can easily be done by taking care of the data frequency. For instance, if we use daily returns in econometric modeling, then annualized volatilities, it will be, right, it will be like this. That means, for example, I know today volatility. We use the high frequency data of the stock transaction data, work out today's volatilities. How can we know the annualized rate? That means if we assume every day it's such volatilities, what's going to be the whole year, the yearly volatilities? How do we know that? The formula, it is this. 252 is the legal working days per year. And the financial markets, we strictly follow that. So this is going to be 252 days. And then we take a square root. That's understandable because remember, if you take the square on both sides, that's going to be 252 times today's, some certain time to any days, standard deviation square, volatilities. And 252 is number of days. Of course, the number of days times per each day, the volatility will be the whole year. And I take the square root. That will be easy to understand, right? This volatility, you can, for example, use the the data you're given, or you can estimate using the model we were going to introduce in the recent 2 weeks. So if we know the monthly returns, for example, if we know the April or March I just finished, we know the March returns, we can analyze that by take the square root of the 12 months, right? So that should be straightforward. Next, the points we want to mention a little bit here. You want to pay attention to a little bit here. So we want to introduce the basic idea of econometric modeling. We want to look into the modeling of estimation of the future volatilities. Firstly, the shocks of assets returns are not serially correlated, but dependent. That's one might be confusing. I will give you several seconds to let you to sense by your own self what exactly meaning there. So I think this is relatively abstract, even for me. Okay, so let's take it for granted. That means the shocks of the assets today, for example, it depends on the past, but they are not correlated. If you want to calculate the correlation between them, you can only probably think about this way. So implying that the theory dependence in asset returns is nonlinear. Okay.
Professor, I have a question. I just found my notes, so it's a little bit random, but I'll ask after you finish the shocks.
Can you say it again?
Oh, I have a question. It's a bit random, but I was gonna ask, really describe the relationship between the series. When I was doing the homework and everything, I've already submitted it. It's just like, what do we look at, you know? As in, we use the p-value. It's not related to what you're teaching right now, but
So you think I still don't understand your question. So you mean what, for example, what the keywords you're talking about, the serial correlation?
yes.
The serial correlation simply means the ACF, autocorrelation function, remember?
Right.
Yeah.
So that's the only thing we would use to describe a relationship between a series?
Yeah, that's interesting. They haven't give you the answer. In what situation those volatilities are not correlated but dependent? That's when it's very abstract. You probably if you don't really understand what the meaning of that, you don't need to do that. So next we'll introduce the model. But if you can understand, will be good. The reason is that the volatility between today, yesterday, or the previous days is nonlinear. Nonlinear is that's dependent. That means, for example, say yesterday or the days before, the volatilities might be related or associated with the future volatilities associated with that in a nonlinear way. So if it is nonlinear, then the correlation will be really weak. You know, that's a little bit abstract. I don't know if I can make this relatively clear.
It's making sense.
Yeah. So, in the how to describe the relationship in the exam. Okay, never mind. So in the exam, I would definitely not test you this. This one is just to give you idea, the intuition between the modeling we're gonna see. You know, so that's the things, right? So that means, for example, today's and the last week's volatility, it might be some nonlinear, like a square or to the power of a 3, some, you know, whatever the crazy functions, their relationship, they're dependent. But since there's such a nonlinear and a crazy format, we never known, the correlation is pretty weak, right? So this is the kind of things. Okay, anyway, so what if the structure looks like? The structure is like this. I think this one we should probably get familiar with. RT is represents for each time. You can see each day, for example, the returns. All right. Mu T represents the mean average. And AT, you can think about like shock. It is not volatility. Be careful with that. This is just simply a shock. Okay. And for example, if you want to estimate what today's performance, today you get a returns. Today you get a mean value. So that means for the today's, you have 1,000 of the observation of the stock transactions. You calculate the mean value of them, and you calculate the shock of them. And the shock is a little bit unobservable, so we use the model to estimate that. So for the mean value, it'll be simply a constant plus the previous returns minus some time lag together. This is a kind of an AR, autoregressive, and this is kind of a shock in the previous days. Okay, so this is the basic structure. I want to re-emphasize the intuition here. I just don't want you to really remember or calculate by hand of those mathematics, but just I want to just re-emphasize the intuition behind this. The first function is a level function. Simply tells you that each day's return can be decomposed mean level and uncertainty levels. All right. So in the next, I want to express the mu t, because mu t is more like a trend. It's more like a expected drift. So I want to model the mu t. And remember, we used the ARIMA model. We used it before. Remember, AR is here, right? That the mu t depends on the past days observation or past months, whatever the units you want to define. And this is a moving average, the previous shocks or residuals or arrows, right? You combine them together to make the prediction on the next period mean levels, right? You never know that. So this is the basic structures. Okay, so the volatility models are concerned with the time evolution of this one. Okay, this is volatilities, right? So this is volatility. We understand this is a variance, and the variance will be RT. The today's volatilities will be definitely depend on the volatility of today's. All right. FT minus 1 represents given all the information we obtained since the last periods. That's why we see this as conditional volatility models. We know the information has been since the last periods, okay? But for today's, when time equals t, do we know the information? No, because we want to predict. We never know that. The shock AT will not come until the end of today's, right? Since we have never experienced that before, we are probably in the yesterday, we don't know that. All the information we can get is stop at yesterday's, right? Okay, for example, this is a time plot of the daily VIX index from 1990 to 2017. So we understand the VIX is basically an implied volatility calculated from the Black-Scholes models. All right, as time series, you simply use the each day's true call price, fit into that Black-Scholes model, and work out what is the volatility implied from the models, given other parameters you know, right? And then you will find that. So you can see the VX, the volatility basically can matter the market panics. To name a few, you can see, let me see what's going on here. 2028, when the financial crisis happens, it's pretty high. All right. And when the 2000, at this periods, when the technology bubbles, internet bubbles happens, the panics a little bit. But you will find recent years, the most recent years, the financial markets panic increases. It increases much more than before. right? So this is a trend. Okay, for example, so I just give a very example to purposely to look into what the model looks like if we can successfully predict and work out the problem. Say for a daily closing index of the S&P 500 index from January 2007 to 2017. Okay, so the log return follow approximately an MA2 model. Now, in your mind, just try to as quickly as possible to recover from your previous memory about moving average models. All right, so let's assume the return of the stock follows the MA2. This is a moving average because this is only the residuals previous shocks here. All right, and this is MA2. This is 2 periods lagged. All right, and this is standard deviation. This is the volatilities. All right, so the residuals show no strong serial correlation, plot not shown, because after these regressions, right, you can get a residual. You want to check if the residual is serially correlated, use the ACF autocorrelation function. And if you find there's no significant correlations, you can see the model is survived, right? And let's assume the model is survived. So this is the time, the residuals, and we find the residual is kind of a randomness. So the model is a kind of like it's acceptable, all right? No serial correlation as time passed by. Okay, but if you look the log returns of the previous models, is here, okay, of the previous models, and if you plot the ACF here, now you will find that the residuals take the square root, right? The volatilities is highly correlated. It's highly correlated. So in this case, we need a model. So that means we can't leave it there. We need a model to describe why there is slowly decaying trend here. That means non-stationarity. We need to figure out the regression models. So that's basically our task, all right? So let me look at this several interesting questions. So the residuals are shown in figure 2. Let's go back to figure 2 here. This is residuals, all right? And is volatility constant over time? Is constant over time? No. Sometimes it kind of fluctuates in some sort of range, but sometimes very high, but still every day is totally different, right? And also we find that volatility could be clustering. This is probably one of the most important findings in the past years. Clustering means when the market by itself, by and large, is more volatile, the volatilities will be concentrated in this period. When the market is quite relatively low uncertainties, in the whole period it will be pretty low uncertainties. So the uncertainty by itself is a clustering, concentrate on some times, right? That's probably another riskiness you want to be aware of that.
Sorry, can you say that again? Clustering means that the market is low uncertainty, so it will use the little data that it has to cluster and focus in one period.
No, it's too complex. I'm not saying that way. The clustering simply means that the high volatility, you know, the similar volatilities will be concentrated on some days. The trend is still kept. So for example, in this figure, right, in this figure 2, right, in this period, when time equals 500, you can say the high volatility is concentrated in this area. This one's pretty high, a little bit high, a second high. So the high volatility sometimes is concentrated in some certain period, not evenly distributed. You know what I'm saying? And for low uncertainties, low uncertainties also concentrate on some period. There's no like a regular, say, high volatility, low volatility, high volatility, low volatility, such as evenly distributed like a seasonal. No, the volatility in a certain period, the high volatility will be concentrated to some certain period, right? It's also very intuitive, right? For example, in the pandemic, in the past year, the stock market's VX index pretty high, concentrated in some certain period. As time passed by, the pandemic, the, uh, the, the, the market panic will be decreasing or decaying as time passed by, right? So you will see that sometimes the high volatilities will be concentrated in some certain period, and we call that the clusterings. That's the thing.
Great, thank you.
No problem. So how to model, that's what we're gonna talk about next. Okay, and so you don't need to care about the short and the small stuff that we were gonna introduce later on. So put simply, we will introduce several models. Because in the past literatures, people talk about different models. All right, so today the model I'm gonna talk about probably this so-called autoregressive conditional Henry square testing models. Trust me, in most of the cases, you don't need to remember those names. And even you ask any professor doing this field and ask them what is the ARCH full name, I'm pretty sure some of them cannot be speak up. Or even sometimes if you want to interview some candidates for some job, they can't speak up. This doesn't matter. You just need to understand ARCH model is kind of a way to modeling the volatilities. Okay, and the format will take the autoregressive. That means volatility we assume will depends on the past histories, its own. Okay, and in 1982, Engel developed this method. I think he also got Nobel Prize for this one. So that is why it is so important. Later on, Boleslav, which is another famous people in 1980s. I'm not sure if he got the Nobel Prize or not, but it's very famous. He got a generalized arch, which is based on the arch model developed by the Engel, which is a Nobel Prize winner, and they developed a more generalized versions in 1986. So you can see the knowledge we learn here is, yeah, it's outdated, but it's still relatively new. Particularly remember the knowledge we learned in the undergraduate classes, the finance, mathematics, statistics, actually, those are already been hundreds of years ago, like in the Newton period, right? It's very far long ago. So those methods were introduced today is relatively new, all right? There's some other methods we were gonna root out. Those are only for the people really research in this field or do the work in this specialized field. People look into that. So we are focused on only the first one and the second one in this masters. All right. Actually, to be specific, I personally, in my research or project, I never touch the others because this is my topic is not quite closely related to this part. Right, so in this case, those are I'm not tapping into too much. Okay, so those things no, like that means we only want 1 and 2, but in the literature, people has developed a lot of methods, but all of them only simply depends based upon the first 1 and the 2. That means arch and the Garch models. The others is just simply extension on that. Okay, so let's formally introduce the first famous model, the arch models. Okay, if we want to predict volatilities for any arbitrary certain time t. Okay, so we assume like this. AT, remember AT? AT is simply the shock, right? The shock. And you can think about like recent 2 days. What's the differences between the recent 2 days returns, except for the mean difference? Then the rest of them will be the residual difference, and the residual difference will be the shock, right? So the shock we can express as some volatility times some random numbers. Let me introduce a little bit here for the small. I think some of us, if we never touch this, it will be abstract. It's kind of like this. Can anybody tell me for this short equation, AT equals to sigma t times epsilon t, which one you can observe from the market?
The data,
For,
probably. And the shock of previous days.
okay, that means you say AT minus 1 is observable, right?
Mm-hmm.
Okay, perfect. So that means the previous days shocks we can observe. Okay, you probably listen. You don't need to observe exactly the value, but as in general, the information, what happens yesterday, you know that. And AT is what we need to estimate. All right, the new information, because we want to make predictions. So sigma t is kind of volatilities. This is a nature of these assets. Some assets by itself it's very volatile. For example, derivative. Some assets is very low volatility. For example, like a bond and a fixed income. This is their nature, and you never know. You never observe that. Okay, and even you know the volatility by itself, this value, the next period, the movement also depends on randomness, right? The market is random. It could be up or it could be down. If it is up, you need to add this volatilities to reach a new high level. If the randomness is negative, that means you need to reduce the previous value by the volatility levels, right? But you can't control the randomness. It's out of your control. So that simply means that your inherent nature, the volatility times some randomness, and together they can decide the shocks with the value of that. Okay, now, since the AT is we want to predict, and epsilon t is kind of a randomness. So I think our only task is trying to predict what is the sigma t's, standard deviation. And especially we use these models. All right, the sigma t square, the volatility equals to the alpha 0, 1 to the n is the constant. And the function of previous days observed shocks, right? Shocks. You can say, okay, so can I use the replace the A with the standard deviation sigma, sigma? No, sigma is unobservables. So we need to replace with the observable values, the information shocks in the previous days. Then the previous days that we can predict what the next period volatility could be, right? That's similar to the autoregressive format. But be careful, standard deviation and A, they have different meanings, although some similar components inside. And here we introduce the epsilon t is a sequence of the IID, random variables. IID means independently and identically distributed, white noise. It's a purely randomness. You just remember this, that's it. Nowadays, the computer software can generate random numbers very easily.
Sorry, Professor, can you
Yes.
tell me again, because I understand that since we're looking for sigma t, because that's all we can figure out, what is the first factor right after the equal sign mean? Yeah, because I don't know what that, yeah, what is that?
The alpha zeros?
Yeah.
Yeah, this is a constant, just simply a necessary factor in the every regressions. That's it.
Okay,
Intercept.
so this is not something that we would be given. This, do we just assume, like, if we, let's say if we were doing a numerical problem, would we be given that, or would we just assume it to be 0?
Well, I would like to say if you have the real data and put into the R Studio and estimate that, I think R Studio will automatically figure out if there should be a constant or not.
Okay.
Yes.
Okay.
Or by itself, you can say R's alpha 0 simply means that if in the previously there's no uncertainties, right? No shocks, 0, 0, 0. What's gonna be the next period shocks? They're still there.
0.
Yeah. Well, I want to say that's probably very less common. All right. Why can you so sure next period shocks there's something there? Right. So that's definitely an interesting question. So Later on, we will use the model to find out using the RStudio computer to do that. Okay. We have introduced, this is sigma epsilon t represents the randomness. Usually we call them standard normal distributions. Okay. Here, I don't want to extend too much, but I think if you can understand your really high level knowledge, I'm pretty much sure. When they talk about the distribution of the epsilon t, they mention that it is the standard normal distributions. And here, when I introduce this epsilon t, we also talk about it is the IID, independently and identically random variables. So my question is that, do you think the independently, identically distributed random variable is equivalent to standard normal distribution? Do you think they are equivalent to each other? That's an interesting question you want to explore by your own self if you have time to do that. But here I just want to skip that. You don't need to do such a learn such deeper stuff, right? I just want to mention this. I just coincidentally find them, put them together here. Just I want to differentiate a little bit. So the now next, let's look into some properties. And those properties, although is a little bit boring mathematics, but I think most of them are not so easy to sense the results, what it looks like. So let's starting from very easy, the ARCH1 models. That means I believe that this regression will be truncated at AT minus 1, right? Only truncated there, right? So like this, we just rewrite this, right? That means today's volatility only depends on yesterday information, okay? There is a beautiful name for that. We call the Markov chain. If you remember, if you ever heard this about Markov chain. Why do we call it Markov chain? Markov chain simply means that the future day's information or movement simply depends the previous day, but not beyond that. It's not depends on the 2 days ago, 3 days ago, no. Just on the yesterdays. All right, so for example, let me give you an example. So do you think the weather is like this format, like a Markov chain? I mean, tomorrow's weather, do you think tomorrow's weather will depend on today's? Might be, because we know that in the raining days in New Jersey, if the recent, today is raining, probably the next day is still raining or cloudy, half, but sometimes also sunshine. All right. So do you think that tomorrow's weather will depend on 3 days ago? Well, the less likely. All right. So in this case, let's just give you an example on that relationship. So alpha 0 larger than zeros and alpha 1 larger than zeros. Okay. And so expected value of AT equals 1. Can anybody tell me why it is that? Why can I say so? Why the shock in the next period? Definitely we don't know today. It's next period shocks. Why the expected value equals 0?
Tomorrow, isn't it because it's unknown, so we don't know what it is?
Okay, it might be intuitive to say so. Okay, but mathematically you will know this. Actually, when you take the expectation, remember this is a randomness, and this randomness, as we define, is a mean 0 and a variance 1, right? So this is mean 0 when you take expectation is 0, so 0. Or you can say the residual risk is kind of like unexpected. So let's take for 0 unexpected. Yeah, you can understand in such a way. Let's take the variance. Okay, so in variance, again, so for this, when you take the variance on both sides, you can solve the simple equations. All right, similar to the autoregressive model we do before, right? Alpha 0 divided by 1 minus alpha 1, and you can find that you need to make sure that alpha 1 less than 1 to make sure the system is stationary, right? And this one, you don't need to do that. right? That means the fourth order statistical moments. That means average, volatilities, skewness, and kurtosis. But I think we didn't require you to do that, so you just don't need to forget about this one. Okay, so at the M4, you can think about like this way. So since we are talking about volatilities, all right, so this M4, you can think about is kind of like the volatilities of volatility. It sounds like straightforward, although it's a little bit hard to imagine in the real world, because we know everything should have its own volatilities, right? When we talk about the stock price, it has volatilities. When we talk about the stock return, it has volatilities. But if there is volatility, we want to look into, do they have their own volatilities? Of course, yes. This is kind of a fourth orders, M4. But sometimes as the real meanings become weaker and weaker. Okay. And particularly for this one, there's sometimes a meaningful because it represents there is a heavy tails. What do I mean by heavy tails? That means it is normal. It is not normal distribution, right? That means each side maybe have a relatively larger areas, right? So the advantage of these models, the advantages of the model is that it's simple, all right, and generates volatility clustering and heavy tails. Let me talk about intuition behind this too. Why the model has volatility clustering, we haven't mentioned that. Why can they generate such a pattern? And why they can have heavy tails can be described in the models. Remember, what is the volatility clustering? That means if the previous state has high volatility, it's a highly likelihood that means the tomorrow will also have a volatility, right? Where I can find this? How can we say so from the model? I mean,
yesterday's stuff. Like where we examined yesterday, shock would probably show
here,
like in the
right?
previous data, yeah.
Yes. So if the previous state your shock is large, then obviously your next period's standard deviation will be volatility will be higher, right? It can easily capture the clustering effects there, right? Okay. So what is a heavy tails or hypertusis? How about let's simply take the Wikipedias. Say heavy tails. Heavy tails. Scale. So let me see. I try to take a very sorry. I just simply say the skewness, maybe better. Yeah, that's better. So let me see if we have. Gee, there's too many mathematics. Yeah, let's just simply look the Google the picture here. All right, so you can say I just simply do the Google picture here, right? That's kind of a heavy tail. This is the normal distribution, right? This is normal distributions, and the skewness is zeros. And if you look, this is negative skewness. That one you can find that means positive or larger values on the returns, for example, more chances, because the area under this curve we understand is a cumulative probabilities. And the heavy tails, you will find that this one is kind of like this shape, or positive skewness, all right? Most of the weight focus negative, and the heavy tails here, right? So this is the represent the skewness here. So let's go back to here. And heavy tails is described under these formulas, this formula. Okay, so we basically calculate the moments, the skewness, the moments of these calculations and work out these results. We don't need to care about the derivations. Okay, why can we see so we have a heavy tails? Because it is positive, right? So alpha 0 positive, alpha 1 positive. I think this is as we have already assumed. All right, and since alpha 1 between 0 and 1, remember, which is here, under the second assumptions we have done before. And here, if we add another assumptions, we assume that alpha 1 squared in this range, that means this number will be positive. So that means there's some heavy tails. All right, and let's go back to the assumption here. Why we want to assume a alpha 0 larger than 0 and alpha 1 larger or equal to 0? Why we take this assumption? You probably think about economic intuition. Because if the alpha, so let's say first look at the alpha 1. If the alpha 1 less than 0, what happens? It's negative.
Would that mean it's skewed to the left? Or like it has a longer left tail?
The thing that
Or
if
no?
if the alpha less than 0s, that happens that the larger the yesterday's volatility, the smaller the next period's volatility is, right? Because it's negative. Is that correct? It's totally reversed, and it does not make sense, right? So that's simply mismeanings. And alpha 0, why not should be negative? If it's negative, can alpha 0 be negative? No, because volatility is always positive, right? So that's the things. If alpha 0 equals negative, that means even there's no information yesterday, the standard deviation, the volatility is negative. No, the volatility has to be positive. So why we assume that both of them should be positive here. All right, just to top us intuition. Let's look at the weakness. The weakness is symmetric between positive and negative prior returns. Okay, let me introduce like why we say so. The restrictive provides no explanation, not sufficiently adaptive in predictions. Okay, so let's continue on that. So you can see we spend a lot of time on the intuition and explanation and the modeling. And next step, you can see the topic we're gonna building the truly arch model in our studio, coding them, and then get some results. But before that, we need to understand each element here. Okay, let's look at the weakness. Why we say so like a symmetric between positive and negative prior returns? Why we say so? Let's look at it here. Look at this equation. Let's forget about the constant. It's not so interesting. Let's focus on this one. This one is simply means next period, the shocks. Well, depends on the previous prior shocks, square, volatilities. All right. Now, the question is that when we take the square, we lose some information. We lose the directions. It's positive or negative. Because whatever, now think about the stock price movement, right? Sometimes they move up, sometimes they move down. But if the magnitude is the same, when you take the square, they are the same. All right. However, now think about this. The intuition tells us when the market is bad, sometimes volatilities, the panic, the uncertainties actually very high. When the market is very good, sometimes the uncertainty is low, right? If you think, remember from your daily lives, it may or may not be written into the textbook you have seen before, but it's the truth. The volatility usually happens or clustering at bad times. All right, low volatility is usually concentrated in good times. So if it were the case, do you think the model can capture that? No, because in this equation, everything's square. You can't identify up or down, right? You can't identify the good time or bad time. So that's the things. I think if you really want to do correct that, you want probably want to change this item. Say, if the previous t minus 1, the information is positive, that means stock price goes up, the alpha 1 should be some small numbers. If the previous period is the negative, price drop down, it might be amplifying the information shocks. All right. So this is such things. All right. So for example, if the yesterday's stock market has panic, like drop down 3%, I'm not sure if you have any idea on that. Usually the stock market is a drop down larger than 2% will be big news. 10% will be the threshold. Fed Reserve will begin to cut off the stock markets. All right, I think the pandemic last year we experienced something like a 10%. I'm not sure 10%. Yeah, there's something 10%, 2 times, right? The stock market crashed a little bit, and the Fed Reserve stopped that, the tradings. So that means if the previous stays negative shock, and highly possible the next periods will be even negative, right? So directions doesn't matter here, and this model fails to capture that. And the restrictive, I think this is a 2 week, so let's forget about this. Provides no explanation. That's the other things. That means all of our time series model is a purely empirical model. That means there's no theoretical relationship. What does this mean? So for example, I just simply means that, okay, so the next period shocks will be the linear relationship of the previous one. People will ask, why you say so? Why you take this format? Why it is not, for example, the a to the power of 3 to the power of 4? All right. Why we now say add some other crazy terms like a sine, cosine, something like, or exponential, a log, whatever. Why it is not log? Like log sigma squared equals to log, right? So we just take it for granted. Let's assume this is simply a linear regressions, linear time series regression, similar to the autoregressive process we introduced in the early stage in this semesters. All right. So this is assumptions. So no theory to back up that. So far, I want you to think about it more deeply in the finance. What kind of finance model we have touched so far has theory foundations, and which of them don't have theory foundation but very useful? Just I'm wondering about if you in your mind you can have some idea on that. So of course, what kind of the model we learn, it has theoretical foundations. For example, CAPM, capital asset pricing model, by the Markowitz, all right, William Sharp. So those people use the portfolio theories. That means if you're holding enough number of stocks, the risk needs will be diversified, all right? Only systematic risk or beta will be held. So this is the CAPM how to derive from. So they have a very solid theoretical background. And the Black-Scholes model, for example, Black-Scholes model is derived from the randomness, stochastic mathematics, integration. All right, so they have a theoretical background. For other models, for example, here we talk about the arch models and autoregressive models, right? They don't have a theoretical foundations. People just simply think about that way and to testify if the coefficients can make the model predictable, right? Okay, so the next, I'm going to talk about how to build an arch models. Okay, let's look at the several steps. I'm not sure. I think today we have some time, right, to present some examples. Building an arch models. So first one, so modeling the mean effects and testing for arch effects. So in a separate PDF file, test arch. So let's go back to the Blackboard. Go back to the Blackboard. And yeah, here in the lecture 7, here, we have a test, we have a VOL volatility PDF. This is the lecture sheet we discussed today. We also have a separate one, test arch. You need to read that page, and I'm gonna introduce it next. So this was the first step. You need to testify if there is indeed an arch effect there. That means the relationship indeed as the model describes. Then you can use the arch models. All right, so you test the hypothesis. If the null hypothesis that no arch effects or there's an arch effects. All right. And when you test them, of course, we know that the R will give you easily that identify the p-value. However, in your mind, you probably will know this is the chi-square, the statistic. You want to compare some threshold value, but nowadays software usually will give you the p-value, so you can easily identify if it is reject or not. Next, order determinations, right? Similar to the model we introduced before, you want to decide which order you want to cut off for the lags. All right, and then you want an estimation. Estimation simply means the estimating was the coefficients for the models, like alpha 0, alpha 1, we mentioned that. And then usually we use the maximum likelihood. That definitely is way beyond our structures, because our studio already give you, every software nowadays will give you directly the results of that, the coefficients. So you don't even care about what happens behind the stage, what happens, what kind of estimation methods we use. You don't care about that. Remember, in the undergraduate statistics, we truly learn one way to estimate the parameters, the least square method. All right, we just minimize the deviation of the fitted points to the real points. By minimize that, we take the derivative with two coefficients and get the value of that. So that's the least square methods. Now here we use the minimum most likelihood, so you don't care about that unless people really do some econometric statistic or look into the details. And the next we want to checking, right? Checking. So checking for the residuals, most likely the residuals. And track the residual distribution if it is indeed means that there's no missing information we need. Okay, so software, we use the R with the package ifgarch, and now in our software you will find that there's a way I might be a little bit uncomfortable so far still. They have a lot of packages, right? Because we know this is a free software, has a lot of the people actively contribute the codes there. So if you want to categorize, you can use the author suggested fgarch, but there are also many other packages already incorporated into the garch estimation. So there may be sometimes a conflicts. So when you install them and call them, the computer will give some warning. Okay, this one will be installed in the newest version. This one has been mocked by other versions, something like that. That means this function has been used by any other functions, but you don't need to worry about that. It's just simply the replicate overlapping. Okay. So firstly, I think today we're gonna focus on the first one. How can we test the arch effects? All right. So you can put out another file. Okay, so this is testing for arch effects. So what happens before that? So let's say this is the AT square, right? Each time T was the shocks. And this is the past periods shocks. Now remember, be patient, pay attention to this a little bit different. Here is not standard deviation. This is just simply square. There's a coefficients. So what I'm gonna do, we just basically test the two hypotheses. One is all the coefficients equals to zeros. That means there's no arch effects, right? That means the next period shocks one independent upon the previous ones. Okay, and of course, the alternative hypothesis will be either one of them not equal to zeros, right? So we will use the F test. I would like to say, if you're really fan of bad statistics or still remember that, you can look into that. But if you feel uncomfortable, you can skip over that. That's fine. Okay, but you need to understand what is a hypothesis, right? What is the equations that we will use to characterize the decisions. So let's take examples on that. I think the textbook uses examples about the Intel, the companies, right? The Intel corporations, stock returns. Okay, so so for example, this is Intel. Let me see what happens here. Okay, so let me talk about this here. So firstly, there's a mean equations. There's mean equations. Let me talk about why this is mean equations here. Let's go back to it is here, right? It is here. Now, when you estimate the entire time series, you want to start in firstly from the returns equals to mean value plus decompose the mean value and the shocks, right? Mean value can be regressed with ARMA model, and the standard deviation can be regressed with arch effects. All right. So firstly, you need to tell the computer what's the format you want decomposed between the mean level and uncertainty levels. All right. So in this case, why they were gonna start to do this? Okay. So they simply assume that the R bar is represents the mean, represents the means. Okay. R is the sample means. That is the way we calculate the volatilities, right? Remember? So remember, if I give you a lot of observations, how to calculate the volatilities here. You simply calculate the mean value across all the periods from 1973 to 2009. You calculate the R bar, right? And each returns minus this R bar, you will get a deviations. All right. So in this case, this is what we call the mean equations. Okay. And a YT is an estimate of AT. So in this case, YT here, it simply represents a kind of a shock. You can estimate that. All right. So you will have A1, A2, A3. So why it is R bar? Because in our the class lecture, we have introduced that. So usually the return should be decomposed to mean level plus the shock level. We need to know what is the mean level. So in this case, we assume the mean is the same for all the days. And obviously it is not a good idea because we know that the mean value for each day might be a little different. Depends on the observations, how much observation you have. All right. You also could be say, okay, my mean value in the next periods is the same. It's okay. You can do so. Then the next will be up and down. attribute to the volatilities. All right. In that case, the mean will be not a function of t, never change. It's simply the average of all the observations, right? And then in this case, you can work out to the square of that, right? To the square of that, show if there is arch effects, right? If there are arch effects, that means you need to work out this one. You need to work out. That means you need to get the data. You need to get the data for the next period's shock square, previous periods volatilities, previous periods volatilities, right? You have all the data, AT minus 1, AT minus M. Then you can estimate if there is a relationship among them to look at the coefficients, right? So the first step is that how can we get AT minus 1, the shock for each period? We simply assume, take the RT minus R bar, we assume that the mean level is always the same in the periods. So the deviation will be simply each shocks, each periods, right? So let's look at the R code. You're firstly to figure out the Intel stock returns minus mean, right? You get the deviations. And you take the square. The deviation square will be the volatilities, all right? And then let's testify the 12 lags maximum. We use the box-Lindgren box. Okay, so what they give to you, they give you a p-value very small. What does that mean? That means you will reject null hypothesis. That means indeed there's some arch effects. We can model that way, right? Okay. This one, the next one I want to introduce into a little bit. Sometimes if you use the RStudio software, they only can tell you what's the p-value. Okay, you reject null hypothesis, they say there's arch effect. But sometimes people want to say, since you construct the equation like this, there's a 12 periods, right, shocks. You want to estimate the coefficients. I want to really look into, for each coefficient, what's the value and the p-value for that, if you really care about that. But it is not so important that you do the next step to do the arch modeling. We already testify it is there's something there. But sometimes people really want to spend some time examining, okay, what is the value of each coefficient in these tests, right? So in this case, you probably need the author's write the code by his own self. It's called archtest.r. When you type into that, it will give you all the coefficients of each regressors. All right. For example, in this case, there's going to be like 1 behind, like 2 behind, like 3 behind. They give you the p-values. And indeed, you will find that all of the coefficients, include the constant coefficients, are highly positive. So we're pretty sure definitely there is arch effects here. Okay, any questions so far for our first step, test the arch effects firstly? Now, if you don't have, let's go to the next stage, okay? And we'll go to the order determination. We will use the PACF of the square residuals, right? So before we do some analysis here, we want to introduce the package fgarch. If you go to the Google, right, for example, if you write down the fgarch, there's going to be a many pages. Sometimes definitely we don't have a patience or we don't have a capability to read through all of them. Now here, we just summarize several points here. Okay. The R package ifgarch with the garch feed command. The program is easy to use and allows for several types of innovation distributions. The default is a Gaussian. Now remember, in the Gaussian distribution means normal distributions. Innovational distribution, that means the distribution of the white noise, the innovation. Remember the epsilon, the Greek letter there. So we assume it represents the normal distribution. Sometimes this computer can recognize it as other types of distribution to estimate the models, and then they will give it different results. But usually we assume that the randomness can be assumed the normal distribution will be relatively easy to calculate. Okay. So in the next, we do simple examples here. We want to look into using the ifgarch package to estimate what Intel stocks, the volatility estimation predicting there. Okay. Let me look at how long this is the code here. If it's too length, it might be. Okay, that's doable. Okay, so let's look at the ifgarch package. We call this package and read into the table the Intel stock returns. And again, so the data is very, very simple. It just simply means the time series data, date and returns. That's it. Then we take the log returns. That's sometimes a good habit to want to take the log returns. If you probably forgot why we need to take the log returns. Okay, come on, so you want to go over a little bit our first chapters, right? But sometimes people just do this without thinking anything, just take the log. Okay, and then you will plot ACF and ACF of the square and a PACF of that. All right, so look at where the order is cut off. And after that, you want to test if there is an arch effect. So simply take the square, right? Take the square, return to the square, and we only assume that as far as the 10 periods lags, and we assume the Lynching box test, okay? And we find that the p-value is negative, very negative. Oh, sorry, very small. That means we will reject null hypothesis, and we assume that there is indeed there's arch effect. So then we can use the arch model to estimate the volatilities. So we use the garch fit, right? This function with R has been installed here. Okay, and the people use the garch 30. All right, garch is equals 30. So that means we will include the 3 of its own selves, right, in the first of 3 periods. And data is INTC, which is we have a coin here, right? INTC equals log returns here. So, and when you take the summary of the handler of the whole equation system estimation, you will get this. Mean and variance equation. Remember, when we describe any time series data, we want to estimate the volatility. You need to firstly specify what is the mean value, mean level equation, and what is the level, what's the equation of the volatility levels. All right. So for example, and the mean levels is going to be the data y will be equals or r whatever equals to the Intel returns. All right, and take the arch 30 effects here.
Sorry, the 3 is like the 3 days you said? What is 3
Yeah,
again?
the 3. Look at this. Look at the outputs. Alpha 1, alpha 2, alpha 3. You clear, right? So it's going to be 3 days lags. It represents each coefficients.
Okay, 3-day lag. Okay.
Yeah. So I think omega here represents what? It's the constant, right? I think it is constant. And what is the mu? Mu represents the mean, right? So the computer think about the modeling. The level will be, that means each day returns can be decomposed to the mean plus the shock. And they also give you the means here, which is the mu. All right. So let me go back to the original equation we have for the gauge model here. Wait a little bit. Let me check if the oh, I think it's a little bit confusing here. It is mean and the variance equations. Mu omega alpha 1, alpha 2, alpha 3 is corresponding to this one. This original equations here. At the very beginning. Here. If we can decompose returns equals the mean level plus the shock level, and particularly the mean level can be decomposed to 5 zeros and autoregress returns and the shock returns and the volatility models can be estimated separately, right? So this is the basic structures. And the next class, yeah.
Sorry, is the equation that was like on page 3 in this file the one that we're using to apply the code for the?
Yeah. Correct. You're correct.
Like the one with the numbers?
Yeah, correct. You want one-to-one corresponding to the coefficient there.
Okay, so that's why we have the 3, and it would be different if there was more ATs here.
Yeah, how about let's go continue to on the next. So we will figure out what's going on there. So actually, next class, I think today we probably don't have such time. So next class we were gonna take out the R Studio and we will put the code into that to implement, and you will sense that what's going on here. And here let's just simply read the data, read the output here. Okay, let's look at here. The mu omega, the mu here. The mu is significant, right? There's something, and omega, which is the constants, which is like significant, but alpha 1, alpha 2, alpha 3, they're insignificant. Okay, they're insignificant. So what does it mean? That means we only use the gauge feed, right? Gauge feed, gauge 1, 0 will be good modeling techniques. But you want to differentiate these two things, right? So one thing is that you want to use the gauge 3, 0. You're starting from that, right? Starting from, you just give a try, but you never have no idea if it is correct. And finally, you find that that gauge model is independent about the previous periods, right? So in this case, it goes to gauge 1, 0, 1, 0. That means you basically reduce to only one period, and you do this again. All right, you do this again. Okay, let me look at this. Omega, mu, and alpha 1. And you will find that alpha 1 is significant. So you want to include the 1 lag period shock there. So this is a little bit tricky here. That means if you put alpha 1, alpha 2, alpha 3, that means 3 times lag altogether. All of them are insignificant. So you want to reduce them. You want to reduce, for example, here you want to reduce only the alpha 1, all right? Or you can cut off at alpha 2, whatever. And then you will find until you find that all of them are significant. and you can figure out the coefficients, right? This is the coefficients, and all of them are significant. So let's plot this. Let me see if they give the plot. So the fitted arch one model is come here, right? If you're somebody, if you're confused, like what exactly the equation they're trying to models, what's the format of that? They give you the answers here. All right, they give you the answers here. So that means the return will be equals to this mean levels. We assume this is a constant. It's relatively easy. It's easiest format, I think. Is mu is constant plus decomposed to shock. And the shock can be decomposed a multiplicative relationship between standard deviation and a randomness. The randomness following the standardized normal distribution. And next, we want to estimate what is the volatilities. The volatilities can be decomposed to a constant and a coefficients of the perverse one period lag. All right, so this is the kind of the final answers we have. And the line, now you have a better idea where the coefficients come from. Let's try to look into, you bring this idea of this model back into the codes, and then you will find what they're doing there, right? For example, like a 0.0176 plus the shock. All right, so where is it? Where I can find this? I think it's on the page. It is here, right? It is here, 0.01657. 657. So they will directly give you the mu, right? So you basically write down, this will be different here. Well, I will be check why it's different, but this is the mu, right? Constant mu, then plus the shock, and the shock is the constant and the first coefficients, right? Copy here, right? So maybe, for example, in the future, the assignments, I maybe give you some like code, right? The arch output, let you to write down what is the entire equations looks like. So far you will find here is what is different from what we learned before. In the previously the linear time series models, we never care about modeling the volatilities. We simply try to target to estimating, predicting what is the levels of those observations, just simply predicting their own selves. However, now not beyond beyond that, we also want to estimate what's going to be the volatilities. All right, and here the return is interestingly, the return neither takes a autoregressive nor take the moving average. It is a simply say constants plus a shock. That's it. There's no AR term, no moving average term. And then you can go back to the code and you will find that the coefficient is insignificant, right? In this case. Okay. Next, they do another examples. I just want to briefly introduce that. Remember, when we estimate the gauge models, we assume the key part is here. The key part is here. I mean, the shock, next shock equals to the volatility times epsilon, the randomness. We assume the randomness is a normal distribution with a mean 0 and a standard deviation is 1. That means standardized normal distribution. So sometimes we can assume the epsilon actually follow the t distribution, the student distribution, because sometimes the sample point is so small. And for small number of observations, remember in the statistic class, the teacher tells us the t statistic will be better than the normal ones. All right. So we change the t star, which in R is very simple. Right? R is very simple. That means when you use the gauge models, right? Gauge feed, the gauge models, data is Intel stock, and the standard deviation and trace equals F. You basically let the computer do that. and then they will know it is a STD will be represents the student distribution or T distribution. Let the computer to do that, not tell them. If you don't write this, they will automatically assume you assume the normal distribution for the randomness, okay, for the idiosyncratic process here, right? It's a little different. And we can find that if you take the student distribution, I think the results will be quite similar. Yeah, it's here. All right, if enter the student T distributions, it will be like this. So the return can be decomposed into the constant plus a shock. Again, so the mean is still constant. And your task after the class, you can go back to the codes and find out if there's indeed AR or MA term. And I'm pretty sure there's nothing. It is insignificant. So we drop that. So we only have a constant mu here. Okay, and the shock can be decomposed to the standard deviation times randomness. The randomness, remember, we assume it is a T distribution, not the normals. All right, T distribution. And for the predicting the volatilities, it's going to be constant plus coefficients, very similar to the previous ones, right? The only difference here, I think, is in the first one. It's a little different on the numbers, but the general structure is pretty similar. Right. Okay. I think I would like to stop at today's class and for nearly 2 hours, and because we have introduced so many statistical level, although I have tried my best to avoid that, but I think unconsciously or I have to incorporate into something when we explain the volatility modeling skill sets here. And if you have any difficulties understanding some financial concepts or some statisticals, just please let me know. All right, so in that case we can go through that, and meanwhile please go through the codes, right? And I will check if we have this data. I think the Intel's data, we have that, right? I will upload the data sets, copy this code, or you can write down by your own stuff in the RStudio, run them, see if you can get exactly results, line by lines. Run this, you can get some feeling about that. All right. So and meanwhile, I want to give you some time because tonight, some students still need to submit the exam right before the midnight. So I want to leave a little bit earlier and work on your assignment if you have not submitted. All right. So let me stop here, and the next class we will continue to review a little bit on this and to continue on the Garch models. Okay, so if you have any questions, you can leave here and discuss. And if you have no questions, you can leave the room. Have a good night.
Thank you, Professor.
Thank you.
Okay.
Thank you, Professor.
You too. Bye.
Have a good night, Professor.
You too. Bye bye.